Yep, I think
there we go. Success. Okay, yeah, well, thank you very much, and I'll hand over to you now.
Okay, good. So let me share. So are you seeing now the title slide full screen?
Yes, yep, that's all up. That's perfect.
Excellent. Okay, so thank you for the invitation. It's a shame I'm not there in lecture room in person. Well, I tested positive for COVID yesterday. It was a bit of a surprise. Now, you know, it's almost out of the news because of very sad things, actually. But yeah, it's just how it is. Right. So yeah, we arranged that I would give this online, as we have become quite accustomed to. So I'm going to give an overview of a topic in theoretical physics called the double copy, and it touches several areas: string theory, particle physics, black holes. And I will, the flow of the talk will be the same as my own path interacting with this topic of the double copy. And I hope that with that you also get an idea of the life of a young researcher. Okay, so so the double copy relates to crucial theories in our understanding of nature. One is general relativity, which is Einstein's theory of gravity, and the other one is gauge theory, in particular Yang-Mills theory, so named after these two gentlemen. Now, in general relativity, space-time is a four-dimensional entity, so three spatial dimensions, one time dimension. And it has a geometry that describes then the effect of gravity. So if that geometry is flat, then there is no gravity, there's no gravitational force, but if it's curved, then that causes the effect of gravity. So you can see here in this image, which tries to represent that in a kind of toy way. So far from the massive body, it's flat, and within the massive body curves some geometry here. Now, in fact, in our four-dimensional space-time, this curvature is a four-dimensional curvature. Einstein's theory predicts some amazing things like the existence of black holes and of gravitational waves, which observations are consistent with. And in inappropriate limits, it reduces to Newtonian theory. So you all know about Newtonian gravity to some extent. And yeah, of course, it was perfectly good for several centuries. So there must be, a limit where that reproduces precisely Newtonian gravity. And that is a limit when the gravitational field is weak and where you have, say, slow motion of massive bodies and also slow time variation of the space-time. For instance, gravitational waves do not exist in Newtonian theory. And then we have gauge theory. So gauge theory, you can think about it as a fancier cousin of electromagnetism. And it is a major ingredient in the standard model of particle physics. So that we test, that have been tested for decades in particle accelerators, including at CERN. For instance, it is crucial in describing how subatomic particles are held together. So I'll say a bit more about it. So the idea of this talk is that there is some sense in which gravity is the square of gauge theory, or the double copy of gauge theory. Now, why are people interested in this idea? mainly for practical reasons, in that calculations which are very hard in gravity have counterparts which are still hard, but easier in gauge theory. So the idea is that you do a calculation in gauge theory, you obtain some result, and then you import that result to gravity in a certain way, and you import it twice as a kind of product. It's more complicated. So I mean, the square is a kind of simplification. But basically, there are two copies of the gauge theory result giving you the gravity result. And this connection between gravity and gauge theory was discovered from string theory, as I will describe. Okay, so let's start with the way that I encountered this topic. I was in Copenhagen about 10 years ago for my first postdoc, and I was working mostly on black holes. So here is an image of a black hole. So a black hole is a region of space-time from which nothing can escape, no information can escape, and well, nothing can travel faster than light. So if light cannot escape, then nothing can escape. So if nothing can escape, that's why it's the black hole. But here, of course, you see some light around it. So this is matter that is around the black hole in an accretion disk, a bit like the rings of Saturn. And what you see here is actually something very interesting, that you have this accretion disk here in the equatorial plane, and but you also see this light, it's a bit weird, on the top and on the bottom. What you're seeing is actually the part of the accretion disk that is behind the black hole. But because the black hole, the gravity of the black hole bends the light propagation, it allows for the light that is behind the black hole to be bent around the black hole and then to be received in your eyes or your telescope. And this image is an actual observation by the Event Horizon telescope. And yeah, it looks a bit like this one after a couple of drinks. Okay, so these are astrophysical black holes. So this is based on actually a computer simulation of the propagation of light from some accretion disk, and was actually used in the movie Interstellar, that had some people who actually know the topic to come up with simulations for this. I think just the light is made more bright here just to make the picture look nicer than what it would actually be. Anyway, in both cases, the light that you see is some matter that is surrounding the black hole. So it's outside of the black hole. Now, the black holes that I looked at were not these astrophysical black holes. They are black holes in higher space-time dimensions, which are motivated by string theory and other scenarios. So black holes are just solutions to the Einstein equations with certain properties. And you also have such solutions in higher dimensions. Actually, they're much richer in a way. You can have different topologies of the event horizon of black hole rather than just a spherical topology, as in 4 dimensions. It's 4 space-time dimensions. So yeah, I was investigating things related to that. Now, across the corridor, there was another postdoc, a bit more senior than me, Donald, and his expertise was in particle physics on the theoretical side, including gauge theory. And well, we do what postdocs do. So you finish your PhD in a given topic, and of course you continue to work a bit on this topic, but you also want to branch out and start new collaborations. And this often happens over meetings like tea and coffee, so some time in the morning where people meet and just talk about anything. And Donald came to me and asked if I'd heard about this idea that gravity was the square of gauge theory. And well, I mean, I never heard about this. It sounded a little bit exotic. He went further and he asked that maybe a black hole is the square of something. So to be the black hole would be like on the left side of this expression. So there will be something whose square is the black hole. But you know, what does that even mean? Take a square root of a black hole? well, I was not convinced, but we continue to discuss, and eventually we work on exactly this question. Right, so let me just give you some panorama. So there are some gravity people working on topics in gravity, and of course there's a big range of that, from the more mathematical ends to the experimental ends, now for instance with gravitational waves. Same thing for particle physics, from particle physics experiments, theorists who are mainly concerned with models that can be tested in forthcoming experiments. We call them phenomenologists, and then people on the more formal side of the theory. And string theory links both. So it's not the only link, but it's definitely connecting to both sides. And what it does is that allows us to look at these sides in a different way that comes from string theory and not in the traditional formulation of gravity or the kinds of theories that we consider in particle physics. Yeah, maybe it's a question for you whether you find the reasoning for the color scheme in this slide based on my accents. Okay, so gravity square of gauge theory. Macroscopically, what this is actually expressing is that the way that gravitons appear in calculations in gravity is like a double copy of how gluons appear in calculations in gauge theory. So gravitons and gluons are the force-carrying particles in gravity and gauge theory. Now you know, at least most of you will know about electromagnetism. You learned about the Maxwell equations. Well, the electromagnetic field is actually made of photons, but when you have many photons together, you can have a continuous field that satisfies the Maxwell equations. And so photons are particles of light. And in Young's theory, the analog are gluons. So the theory is much more complicated because these photons, well, they interact with charged particles such as electrons or positrons, but the photons do not interact with other photons, whether gluons do interact with other gluons. And that makes the theory much more complicated. And the same happens for gravitons in gravity. So gluons are a closer analog of gravitons, and they indeed somehow are the basis for this relation. Now, in particle theory, the type of calculation that people are often interested in is the calculation that tells you if you have some initial particle that collides and then you get some final particles, what is the probability for these events, as opposed to the probability of a different configuration of final particles, different number of final particles or with different energies and directions of motion. So yeah, this is calculated based on the scattering amplitude for these events of going from these initial particles to the final particles. And then the probability is the norm squared of this, is the absolute value squared of the scattering amplitude. Now, these are typically computed in a perturbative approach. So you should think about something like a Taylor expansion where you have some corrections, some small corrections. So there's some leading part of the result described by 3 diagrams. So the way to think about these diagrams is that time is moving from left to right. So you start with 2 particles, they interact in some way, and you have 2 particles at the end. And in all these diagrams, you start with 2 particles and have 2 particles at the end. I mean, I could have chosen 3 particles at the end, but let me just give this example. But then you can also have things happening like this, where your diagrams have a loop or 2 loops or 3 loops, and these are higher order corrections. Okay, there's a toy for my baby. So yeah, let me just, so yeah, in quantum mechanics, what you should do is to obtain the amplitude by summing over all possible ways in which this process of going from these initial particles to these final particles, in which this process can occur. So it can occur in some way like this, where two particles kind of merge and then split again, or here looks a bit like these two particles are exchanging one particle, and so on. And so you sum all these contributions, and this would be the leading part. And this corresponds to the classical part of the theory, and these are then quantum corrections. Actually, this is for massless particles. If you have these mixed with massive particles now, it's more complicated because the loop diagrams also have some contribution to the classical part. If you consider just gluons and gravitons, which are massless particles, so just interacting with each other and not with other and not with massive particles, then you can have this picture in mind. For gluons, when you do this calculation, well, these loop diagrams typically diverge, so they just give infinity. However, there's a way of understanding this divergence. You can somehow absorb it into the description of your theory. You can renormalize it. And actually, yeah, this gives a way of making sense of the theory, and you can then make predictions by calculating the scattering amplitudes. And this is, yeah, what's tested at CERN, etc., particle physics experiments. However, for gravitons, the divergences can't be renormalized. They can't be somehow absorbed in some way. So basically, you would have to correct your theory of gravity outside of what you would start with, which was Einstein gravity. So somehow, quantum Einstein gravity is not a good theory of quantum gravity. You can correct it somehow. So these corrections will be important at high energies. There's a sense in which at low energies you get contribution from Einstein gravity, and then you can consider higher energy corrections. So this would be something called effective field theory, but it's not a complete theory of quantum gravity. So you would have to have a complete theory, you would need to have an infinite number of these effective corrections. So this is the problem of quantum gravity. Right. So this led people to think that maybe particles are just an approximate notion. So we have this series of particles and they work fine in many cases, such as for gauge theory. But maybe the fundamental objects are not particles, maybe they are strings. And so these strings would be extremely small, which means that effectively, in the kind of experiments we can do, we couldn't really distinguish them from particles because according to the uncertainty principle, you have to go to very high energies to reach very small lengths, to probe the physics in very small lengths. And these strings could be as small as 10 to the minus 35 meters. So this scale, this is the order of magnitude of the Planck length, which is a very important unit of distance. Obtained by obtained in this way from the most important constants in physics: Planck constants, G Newton from gravity, and C from relativity. So quantum, gravity, and relativity are all together in this length. And at this scale, for sure, something needs to enter that is quite different from from what we currently know about gravity. And that could be then a description as strings. Strings could be, the scale of the strings could be larger, so it can be larger than this distance, but this is the minimum distance at which something must come and like solve the problem of quantum gravity. So why strings? So yeah, thank you for the question. I'll just come back to it. So why strings? Because these divergences ultimately appear due to the fact that we have point-like interactions. So the interaction, the part, in the interaction is, is meets at a point, but for a string, you don't have this this point-like feature. Say in this diagram, in the particle theory, you have two particles going to two particles. Here we have two closed strings, these circles going into two closed strings, these circles, but the analog is a smooth surface, and the calculation will not give you this divergence that I was talking about. Now, of course, if the strings could be so small, then how would we ever probe the physics that tells us whether this is true or not? And that is a very important question, of course. And so this string, so this is in reply to the question in the chat box. Yeah, it would be great to be able to say whether this is true or not, but the problem is that experimentally, it's very hard to reach the regime where actually these corrections, these quantum corrections in gravity, well, where you could make an experiment that gives us clues about quantum gravity. Maybe there are things in the related to black hole physics, because there's some singularity inside the black holes that also needs some quantum gravity understanding, and also in the beginning of the universe, in the Big Bang, in principle, some quantum gravity understanding is needed there. So yeah, people try to explore how we can obtain clues about this. Otherwise, just having a theory that describes gravity and is consistent with, say, gauge theory, etc., and that can describe all of them, that can unify them into a single framework, which makes sense quantum mechanically, and which is a well-defined theory satisfying basic physical principles, is very hard. It's extremely hard, and string theory does the job. Is it the only thing that does the job? No, I guess we don't know. And there are other proposals which I'm not really competent to talk about. But yeah, so this is the reasoning for string theory. Now there are two classes of strings, closed strings and open strings. And when you consider this theory at large distances, so when you're not probing these extremely tiny scales where you can somehow see the length of the string, they will correspond to different types of particle theories. Gravitons for closed strings and gluons from open strings. And I'm just going to write this kind of incredibly oversimplistic relation, but basically the closed string can be thought somehow as the product of open strings in calculations. And this is at the heart of the double copy. Now, when you consider the particle approximation, then this gives you that gravitons are like the double copy of gluons, and this gives rise then to the understanding of the double copy. But notice that, in this case of gravitons as double copy of gluons, you don't have to think about string theory at all in applying these techniques of the double copy. And in fact, it could have been discovered potentially before string theory, but it wasn't, because string theory connects to these two types of theories in a very special way, provides a kind of a meta structure that allows us to see, to look at these theories in a way very different from their traditional formulations in terms of, say, the Einstein equations or the traditional formulation of Young's theory. Let me tell you a little bit more about this. So let's consider the scattering of strings. So I mentioned before the scattering of particles. So there's some scattering amplitude and the leading order corresponding to summing over 3 diagrams, diagrams with no loops. So here's one diagram, here's another diagram. The diagrams that can happen, let's say the vertices, this vertex has 4 legs coming out of it, this has 3 legs coming out of it. The types of vertex and what they mean exactly are given by the so-called Feynman rules, and these are Feynman diagrams. And basically, each diagram corresponds to a mathematical formula. And so when you then put in the quantities corresponding to the initial and final particles, then you get a number out of a diagram. Now, the analogous calculation in string theory is not based on many diagrams. There's a single diagram, although of a very different nature. So here you have two, let's say for closed strings, two initial closed strings, and there's some interaction, and there's some final closed strings. And the diagram is like a surface spanning these strings, and this is called the world sheets. And string theory is formulated as a theory living on these world sheets. It's a so-called conformal theory, which means basically that the calculation of this diagram can be deformed. So the conformal means it doesn't, it doesn't care about certain aspects of the geometry. So you can actually deform this into a circle, into a sphere, which makes the calculation much simpler. And you can shrink these circles into points. And there's a calculation related to this. So when you calculate the scattering amplitudes in string theory, you have some calculation based on this, on having some points representing the external strings, and then it's a calculation on a sphere where you integrate over the positions. You integrate over the positions of these points. So this is a two-dimensional integration over the sphere, and in a very beautiful paper using some complex analysis, these people were able to disentangle these integrations into a product of two independent integrations over a one-dimensional, so over a circle. And basically, these kinds of diagrams are the analog of these four open strings. So these are actually disks. I made it as like a top hemisphere and the bottom hemisphere to give the slightly misleading idea that you can just somehow, that they fit together to make kind of a sphere. It's not exactly like that, but just very schematically. Right. So in the particle limit, meaning when you are at distances much bigger than the string length, where you cannot somehow probe that there is some string length there, so you send the string length to 0. This actually gives that there's some scattering amplitude for gravitons, which is a double copy, some kind of product of scattering amplitudes for gauge theory. And these people came up with a very powerful prescription to use this at the level just of particle theories, which has been very fruitful over the last decade or so. Again, the goal was to do calculations in gravity based on calculations of gauge theory, which are simple. Now, what about black holes? I've been talking about these kind of particles. What about macroscopic black holes? Do they have a simple double copy description? So as some of you who took the space-time and gravity module know, you can write down in exact formulas describing the geometry of certain black hole spacetimes. So can we write down those formulas for the black hole spacetimes as a kind of a double copy of formulas for gauge theory solutions, so solutions to the Yang-Mills theory? Well, this is what, this was Donald's question. And we thought about this. We made like some tiny progress, but didn't go very far. Instead, we worked on other things related to this topic. But eventually, Chris White came up. I guess you all know him. Chris White came up with some wonderful ideas, and we wrote a paper together on this topic. And the main result is that the geometry describing the black hole spacetime, which is a curved geometry, but you have to find a way to decompose it into a part which is like a flat geometry, so where there's no gravity, and the deformation of that, so deformation of that flat geometry to make the curved geometry. And it is this deformation that is a double copy of something in gauge theory. In particular, something like an electric charge squared, which is an electric charge is something from electromagnetism, but there's also a natural extension of that into gauge theory. And that is the macroscopic analog of this relation, because the graviton is like a ripple in space-time, like a deviation from flat space-time. So it's the deviation from the flat space-time, which can be described as a double copy of something in gauge theory. And I'll just present here these formulas without explaining very much. Some of you who did this module, and I'll encourage others that didn't have a chance yet to choose it as an optional module. Well, here we have a metric. This is an object that describes the geometry of the space-time. There are these space-time indices, which are the bane of the existence of students of general relativity. And the point is that for certain, well, actually for the most important classes of solutions we have, for black hole solutions, you can actually decompose the curved, the metric for a curved space-time into a metric for a flat space-time, so this one, and some deviation. And then this deviation is precisely written as a kind of a double copy of something in gauge theory. In particular, so when you have an electric charge, a static electric charge, that's a Coulomb solution, gives you some electric fields, and there's a different mathematical language to express that based on these gauge fields, which we also cover briefly here in this module. And then you can see that this k appeared twice, so it's like a double copy. The phi is not squared when going from here to here, but this is also consistent with the rules, with the very particular mathematical rules of the double copy when applied to particles. So I mean, I'm not really describing those things in detail because you don't have the background yet for that. Okay, so there are many applications of the double copy. Actually, the first class of applications will have to do with doing calculations in quantum gravity based on these loop calculations. So you want to know, so in Einstein gravity, you get divergences that you can't control. If you introduce supersymmetry and get supergravity, those divergences are not quite as bad. And so people want to study that in detail to see exactly what's happening. And whether, so one question is whether any point-like theory of gravity, so when the particles, gravitons, and some other particles, such as in supersymmetry, you have other particles that form, that are parts that form a bigger symmetry with the graviton, which is supersymmetry. And there are different kinds of supersymmetry, different degrees of supersymmetry. And so the goal was to do loop calculations there to see if those divergences always appeared, at which loop order they first appeared, etc. And these are very difficult calculations, but people have been able to make a lot of progress on this based on this idea of the double copy by doing analogous calculations in super Ingles theory, so some supersymmetric version of this Ingles theory. So that was the first somehow important application of the double copy. And then there are people working on this story that I just described, on doing the double copy of exact classical solutions. So let's say these exact black hole spacetimes can be written as a double copy of some exact gauge theory solutions. Here are some people at the Center of Theoretical Physics working on this, apart from myself and Chris. It's my students, David, and I guess you know many of these people from being teaching assistants or of course as lecturers. Yeah, so this is one kind of application of double copy to classical physics. Now, the Einstein equations are very complicated. So when you can find an explicit solution that you can just write down for the geometry of the space-time, it must be a solution to these complicated coupled nonlinear partial differential equations that are the Einstein equations. When you have more complicated spacetimes, such as spacetimes where you have, let's say, dynamical black holes, you can have like a black hole binary, which emits gravitational waves, and then eventually the black holes approach and merge And it's this, it's this emission of gravitational waves, especially close to the merger point when it's stronger, that can be observed. Then we observe those gravitational waves very far away. Yeah, when you have a situation like this, very complicated, you can't just write an explicit exact solution. You can either put the Einstein equation in a computer doing numerical relativity, and I guess in some module you will probably have looked at solving differential equations numerically. In the case of the Einstein equations, that's quite complicated, but it's possible. But it's also very computationally heavy. So it's good to also have an analytical handle on the problem, and that then applies to some approximates, some approximation scheme. Let's say when the black holes are far apart, you can think about them as some massive particles. And you can do calculations similar to those in particle physics, where the black holes are represented by massive particles and then exchange gravitons between them, which represents the attraction that they feel from each other, and also emit gravitons, which represent the gravitational waves away from the binary system. So these are some people who do, I mean, there are more people doing calculations like this. And also in the, actually, there's a mathematical relativity group in the School of Mathematics at CTP. There are several people, and these people have used double copy techniques to tackle things like that. Right. So now approaching the final part of this talk, I want to go back to these loop calculations, because what has happened is that there's a very efficient way of applying the double copy, so from superunions to supergravity, for loop calculations in particle theories, but loop calculations in string theory are much more complicated, and their progress has been much slower. And so the hope is that we can import some of the progress here into the superstring setting, and that's what I will describe. Okay, so I told you about this sketching amplitudes calculation. There were some diagrams, some tree diagrams. So this represents all the tree diagrams. This represents all the one loop diagrams, which some of the first quantum correction and so on. Two loop diagrams, etc. Now, in string theory, I told you before that all the leading order diagrams, tree level, were represented by some calculation on a sphere. Now, at one loop, the analog is another two-dimensional surface. So these would be all Riemann surfaces, but with a kind of a hole. So this is like the surface of a donut. This is a torus. And in string theory, so at each order, you get a calculation on a Riemann surface of different genus. So the genus is the number of these handles or holes. This is genus 0, genus 1, etc. So the genus corresponds to the number of loops. And when you have your string theory calculation, you can take the particle limit. If you take some limit where the string length is 0, so this parameter alpha prime is the square of the string length, then you get precisely some results in the particle theory that is the limit of the particular string theory that you're looking at. And some results in particle theory were first calculated like this, actually. For instance, at one loop, some calculation like this gives these diagrams in some supersymmetric theory. These are the only one loop diagrams that contributes. Yeah, and this was first done with input from string theory. For instance, for the type 2 superstring, this is just a certain type of supersymmetric string. The particle theory that you obtained in these limits is the type 2 supergravity. And although this one loop calculation, as I mentioned, was first done based on a superstring, actually since then, much better techniques have been developed for supergravity, including the use of the double copy from superunions theory. And these have allowed for a much stronger progress to occur here, where now there are some results at 5 loops. So based on the double copy and other methods that have also been developed over the last 2 or 3 decades. Whereas in the superstring, the higher you go in genus, the more complicated it gets. Oh, I mean, that's also true in supergravity, but here is much more dramatic because the mathematical description of these higher genus surfaces becomes much more complicated, and the current progress was basically 2 loops with very little done on 3 loops. So our goal was to try to find a way of importing this progress in supergravity into the superstring and try to just push up this number here. In the past, string theory helped the particle theory, and now we want to know if you can somehow import the result from the particle theory at higher orders also to string theory. And we can actually do that. That was our conclusion. This is work done with my longstanding collaborator, Yvonne Geyer, and also with my former student, Ricardo Monteiro, my namesake. It was quite a tough project technically, so I hope he doesn't hold a grudge against me because of this. This was a UK talent collaboration because Yvonne has been in talent for a few years. Well, she's an amazing collaborator, a very good friend, but actually during this project, she was a bit annoying. So this project occurred during COVID, during the lockdowns, etc. And this is the typical conversation. Here people are very worried, and I have COVID now, but okay, vaccinated, etc. And everything's a bit mild now, but before people were a bit scared. And you join a meeting with her, and this is what she comes up with. What do you even say to that? How do you respond to that? So yeah, that didn't show a lot of respect. But okay, what can you do? Well, eventually I got over this, and we actually ended up doing some work. Yeah, so she managed to escape Bangkok, where she works, to some paradise islands, where she spent most of the times when they actually had very strict lockdowns in Bangkok, stricter than in London, although probably not as long. Okay, so what did we come up with? Well, it was a strategy then to go from results in the particle theory to results in the string theory. And what we checked is that this strategy works in reproducing the string theory results up to 2 loops, where it was known already. But then we went 1 order further and present a new result at 3 loops. So it's a conjecture, and which means that it has to be independently verified. And the basic idea is that we start with some 3-loop calculation in supergravity, which has been known for about a decade, and it was obtained from the double copy from some analogous results in super-Yang-Mills theory. So this was one of the first quite non-trivial applications of the double copy, actually, this 3-loop result in the particle theories. And then we managed to write it in a way that looks like a string theory formula, but is still just a particle theory formula, but in a mathematical language that is more similar to string theory. And in particular, is based on some surface, which is like a degenerate genus 3 surface. So genus 3 for 3 loops is like having 3 holes. And here, these handles are like pinched. So topologically, this is like a sphere with 3 pairs of identified points. So it's a sphere with 3 nodes. And then the tricky part is to uplift this into a formula on a genus 3 surface that is conjecturally valid in string theory. So this is what we've done. We have some results, which we hope it is correct. And we hope that this idea of importing some results from the particle theory to string theory will help understand better these loop corrections in the superstring theory. Okay, so this was basically what I wanted to tell you. So the main message is that, well, gravity can be described in some particular sense as a double copy of gauge theory. So this has many applications. So you can think about as a method to obtain results in gravity from those in gauge theory. And the range of applications continues to grow from quantum, so let's say these loop results, to different kinds of classical problems, such as scattering of black holes or merging of black holes in gravitational waves. It's related to particle theory, to string theory. So it just brings together a number of topics, which is why I've been interested in it. And finally, there is this fact that although it doesn't rely on string theory, that's how it was discovered. And so this brings home the message that string theory has just been quite useful in creating connections between, let's say, gravity and gauge theory, also between different types of gauge theories and theories like that, closely related theories. So it's just part and parcel of our space of theories, our somehow theoretical baggage of theories. And string theory just fits perfectly right in a very non-trivial way, and allows us to learn very surprising things, because the way it connects to these theories, such as the limit where it keeps Einstein gravity, or the limit where it keeps Yang-Mills theory, it does so in a way that is very different from the traditional formulation of these theories. And so it allows us to look at them in a very novel way. So is string theory the correct theory describing quantum gravity in our universe? We don't know that. But that's not the only motivation to study string theory. And I think that was also one of the messages of this talk. Okay, this is the end, and I'll be happy now to answer questions. I see there's a question in the chat box. What contributions do you think supergravity will bring to field theory in the future? Well, when supergravity appeared, so people had recently digested that that Einstein gravity cannot be turned into a quantum theory for the reasons that I mentioned. And then supergravity, because its divergences somehow are not as bad, people thought maybe actually supergravity does not have these divergences. But then as these calculations proceeded, they realized that yeah, actually it still has divergences. There's the most supersymmetric theory, which is not kind of a realistic theory. That's somehow, it's too supersymmetric in principle to be realistic. But okay, there's still a kind of a loophole there that would be nice to close. Most people think it will still have these divergences, but it would be nice to understand that, because what that would tell us then is that it would somehow confirm the expectation that theories of particles, no matter how many particles they have and how those particles fit in a symmetric framework, as in supersymmetry, where they're all related by some supersymmetry transformations, that no such theory of particles can describe quantum gravity. Yeah. On the other hand, of course, supergravity is also related to superstring, and so yeah, the results, as I argued also here, there's a close connection between all those results, as in the way that supergravity arises in some limit of the superstring. And so to understand some aspect of superstring, then supergravity is relevant. Well, so there is another question in the chat box, asking what are the main challenges. There's this toy from my daughter just keeps speaking by itself. I'm not sure why actually. But okay, the main challenge in quantum gravity is that there is no reason to think that there'll be, it's not a necessity that there will be clues to what is the correct theory of quantum gravity at energy scales, which are accessible not just today, but almost in the imaginable future. Because these tiny distance scales where we know that something must happen, where that would affect, our experiments, are just too tiny for the things that we can probe. But as I said before, that doesn't mean that there's nothing we can do. In fact, there is much that we can do. We can try to understand quantum aspects of black holes, which have some similarities inside, which require some quantum gravity description. In fact, even aspects of black holes that are not just at the singularity may require some quantum gravity description. Also, the Big Bang and early universe cosmology may give us clues. For instance, the theory of inflation, I don't know, some of you may have heard about this, is the idea that in the very, very early universe, there was a period of very rapid expansion of the universe. So the universe grew very quickly. The universe has been expanding ever since, but at that time was a very dramatic expansion. So this is a speculative idea, but yeah, which is well, there are things that are consistent with it, and that makes a lot of people think that maybe this is actually the case. And that expansion brings very small scales to very large scales. So yeah, it brings features potentially of quantum gravity, somehow at the part of quantum gravity that we don't know about, the complete theory of quantum gravity. It brings these features perhaps into larger scales that we can probe by astronomical observations, such as the cosmic microwave background radiation that you may have heard about. Okay, so there's another question, which is whether string theory only produces linear general relativity or the original Einstein's nonlinear. Yeah, it's the nonlinear theory. It does reproduce a nonlinear theory. Of course, it's easier to check. But if you have a module on string theory, then in your one semester module, probably you'll just look at that it reproduces linear Einstein equations, linear Einstein equations, but yeah, so basically the closed string has many modes, so it can actually represent many different particles of different masses. So in string theory, when you write down an effective description in terms of particles, you actually have an infinite number of particles at increasing mass. And that mass is very high because the string length is very small. So in principle, we cannot access these particles, because it will require very high energy to produce those particles. Yeah, but then for at the massless level, somehow the first particle in this tower, because of the closed string, would be the graviton, at least in the superstring. And yeah, the graviton will satisfy the linear Einstein equations, but then you can also develop from that to show that it reproduces the nonlinear Einstein equations. So one way of doing it, which is very interesting, is to do the following. You consider so string theory on a flat space-time, and you find that these gravitons must satisfy the linear Einstein equations. Or yeah, or that the theory is consistent in this flat space-time. But if you put the theory on a curved space-time, if you put the strings, propagating and interacting on a curved space-time, you find that that curved space-time must satisfy the Einstein equations. Otherwise, you just can't put the string on it, So that's the yeah. It imposes then that your space-time is satisfying the Einstein equations, which you can think about as having then a nonlinear gravitational field that must satisfy the Einstein equations. So there's another question. This one is about the relation between thermodynamics and general relativity. Well, so one of the most amazing inputs from black hole physics is so-called black hole thermodynamics. So as I mentioned, the fact that we can't have like from Einstein gravity to have like a make it into a complete theory of gravity, it doesn't mean that we cannot do look at some more limited problems where we can actually put both together. For instance, we can consider quantum fields on a given space-time. So in an approximation where we treat those fields quantum mechanically, but where we have kind of a classical space-time, let's say a black hole space-time. And then based on that, it actually turns out that the black holes are not completely black. They emit some radiation that is a quantum effect, that's so-called Hawking radiation. So that gives the black holes a temperature, because this radiation is just a black body radiation with associated to a given temperature. So those of you who have had already a course on thermodynamics will know about this, about what the black body spectrum is. And actually black holes also have an entropy. And there's a first law of the black hole mechanics where the energy is just the mass of the black hole. And there's also a second law, because the area of the black hole must always increase, at least classically, and quantum mechanically, even if it increases, that's because of the emission of, even if it decreases, it's because of the emission of Hawking radiation. But then that radiation also carries an entropy, so the total entropy always increases, as the second law of thermodynamics tells us. Yes, so indeed, there's a close relation there that has actually had a very profound impact on theoretical physics. In particular, because I guess we discussed it in space-time and gravity briefly, the entropy of a black hole is proportional to the area of the event horizon, whereas normally an entropy is proportional to the volume, let's say for a gas or something like this. So that's led to an idea called holography, which says that that a gravitational system whose entropy is proportional to an area is dual, has a dual description in terms of a non-gravitational system living in one fewer space-time dimension. Because then in that one fewer space-time dimension, in that space, then a volume is an area. So a non-linear field theory in that one fewer dimension is describing gravity with one more dimension. And so yeah, this has been a very important development in the study of quantum gravity, and that has had a very concrete. So again, in that case, people have actually proposed that something like that should be possible, but the only concrete way of implementing it came out of string theory and the so-called ADS-CFT correspondence. Maybe that, okay, there are some other ways that in the meantime also have been appeared that maybe they're not rely completely on string theory, but they were basically inspired by the ADS-CFT correspondence. So where you can make very precise calculations that verify this holographic map between gravity and the non-gravitational theory. So this is a very, very different kind of relation from the double copy. There are two types of relations between gravity and gauge theory, but they are of a very different nature. there's another question which is in the process of being typed up. So the question is about these divergences in these particle physics diagrams, and there are some ways of dealing with that. Of somehow taming those infinities, at least for the case of gauge theory, not for the case, not quite for the case of gravity, where you can. So one of the tricks is to use dimensional regularization, and there are different kinds of infinities actually that can appear in those diagrams. There are some called, let's say, low energy divergences and some high energy divergences. It's a very complicated topic, so I'm not going to go into detail here. But indeed, there's something called dimensional regularization where you go off for dimensions. You take the dimensions of some integrals you have to make that lead to these divergences. So they're four-dimensional integrals, but you take them off the four dimensions, let's say 4 minus epsilon dimensions, or epsilon, then you take to be a small number, in order to obtain a mathematical expression out of it that is not just infinite. And you need to regularize it in some way to make sense of the results. Yeah. And again, we also have mass renormalization, where some infinities can be just absorbed in redefining your the mass parameter in your theory. Right. Yeah. So it's not somehow probably the best setting to go into the details about that. But yeah, thank you for the question. And there's another question here. So there's a question of whether there are other examples of the double copy apart from the Kershel double copy or the Weil double copy. What happened? Okay. Show. So basically, here, this double copy describing some curved space-time in terms of some flat space-time and some double copy of a gauge theory solution. This is the so-called Kershel double copy, because this way of, if such a way of writing the metric exists, this is the so-called Kershel's metric. There are some things that these objects have to satisfy, some conditions. And then this gives a very clear way of relating it to gauge theory solutions in this way. That's the so-called Kershel double copy. There's another thing called the Weil double copy, where instead of looking at the metric, you look at the curvature. So from the metric, you can calculate the curvature of the space-time, and you can express the curvature of the space-time in terms of the field strength of the gauge fields. So again, I'm afraid most of you will not have come across this concept yet. And well, whether there are other examples. I think there are other ways of approaching double copy of classical solutions. And you know, that's just looking at the double copy of relating classical solutions. There are many other applications of the double copy. So in each particular type of problem, when you have like particle scattering, when you have exact solutions, when you have some perturbative solutions representing, let's say, some black holes orbiting each other and emitting gravitational radiation. So all of these, for each of these, the particular way in which you apply double copy will have to be, you know, adapted to your specific problem. So yeah, there are different prescriptions to use this, you know, to see the double copy in different instances. Okay, I hope I answered the question. So yeah, I hope I managed to keep the pace, and it was not a very low energy talk given my current condition.
Wonderful. Thank you very much for giving the talk today, Ricardo. If anyone else has any questions just before we end, there were a few people that had questions in the room, but they logged on and they sent them that way. And we did very much enjoy your some of the humorous slides that you put in there.
It's a bit weird because when you are not in the room, you know, you're speaking
yes.
like sound.
no, that
it's a little bit cringy.
That did get a laugh. Yeah, no, a few times. Yeah.
Okay. Great.
Well, if there are no further questions, then thank you very much for your time, and thank you everyone for coming today. We have one more lecture, one more talk this semester, which will be in a couple weeks' time. So please do check the group channels for that to find out more. And we'll also be posting information about our end of year events and things like that in the coming future. So stay tuned for that. And thank you very much for coming today.
Thank you.
Thank you very much, Ricardo. Thank you.